All right, now we're going to do some weak acids or bases. We just got done with strong, so let's review strong. Strong's ionize 100%, so it would ionize into H plus and Cl negative. If this was 1 molar, it would ionize into 1 molar H plus and 1 molar Cl negative. Well, as you see, we're no longer doing strong acids. We're doing weak acids and bases. This is a weak acid. How do I know it's a weak acid? Because it's not one of the strong 6. So it's going to break apart into H plus and C2H3O2 negative. They tell you that it's a 0.1 molar solution. We don't know what these are. That's what we're trying to figure out. We do not know how much this dissociates. We know it doesn't dissociate 100% because it's not a strong acid. So whenever this happens, we have to set up a race table. So go ahead, minus your reactants, add your products, add these two together, and we're good to go. If there's a coefficient here, adjust your x's accordingly. Your Ka's are products over reactants, so this is x, and this is x, and this is 0.1 minus x. You already have your Ka value right here, so this is what you're solving. You're solving for x. Wow, that looks like we have to do the quadratic. But there's something in chemistry. We are going to assume that this x is so tiny that it's not going to make a bit of difference if we get rid of it, the bottom x. So we're going to make this math problem a heck of a lot easier. And now we can easily solve for x. And x comes out to be, oh, right here it says 0.00133327. You know the pH equals the negative log of that H. So the pH comes out to be 2.88. Easy, right? Well, you can read about what happens if we neglect the X, etc. They use the quadratic here and then use the math button. Press the math button on your graphing calculator. Tab down, and there's something called the solver. And you can plug in your quadratic exactly how it is using the X button and everything, and it will give you what your X is equal to. But we don't need to because we're neglecting this X. When can we neglect the X? Well, we're assuming that it is such a small dissociation. If we take that H plus divided by the original acid concentration times 100, we're assuming that it's going to be less than 5%. Because that's such a small dissociation, that's why we get rid of that X. There is something we have to do if it comes greater than 5%, which we'll talk about, but as of right now, you do not have to do the quadratic on the AP test, so we're going to ignore the X. You can read about why we're doing this, and I'm moving on. All right, so hypochlorite. It says, you can read all this, it says it forms the weakly acidic hypochlorous acid. Ugh, you don't remember what hypochlorous acid is. Problem's ruined. But you know an acid has a proton. So add a proton to this. Well, what's H plus OCl minus? It's just HOCl. We saw it last year as HClO. So we're good to go. Let's write our dissociation. First of all, how do I know what I want to dissociate? It's whatever they give us. If they give us a Ka value, we're dissociating our acid. If they give us our Kb value, we're dissociating a base. They gave us a Ka, so we know we're going to dissociate our acid into H plus and OCl negative. This is a weak acid, so we want to use the double arrows, and we don't know how much it dissociates. That's what we have to figure out. So let's do our rice table. We love these, and they tell us that we have 0.001 molar HOCl. We always start out 0 for this. This is minus X. This is plus X. plus X. Add your I and C together. And this is what you have. Set up your Ka equation, its products. And I think you guys are going to be okay with this stuff because you've been doing it for a while. Like little bits here and there. Like none of this is really new, it's just finally combining all of it. Okay, so this is our equation. Looks pretty difficult. We know that we're going to assume this x is very, very tiny. So we get rid of it. Solve for your x, which is equal to your h plus, and I always write this. Do not skip this step. X is always equal to your h plus when it's an acid. When they give you the Kb and it's a base, it's going to be equal to your OH minus. Make sure you do that so you don't get it mixed up. This comes out to be 5.9 times 10 to the negative fifth molar, because you know brackets mean concentration. And then you know pH equals negative log of H plus. So it's negative log of 5.9 times 10 to the negative fifth. So it's 4.23. Not bad, right? Guess what you get to do? You get to do one on your own. So I want you to pause the video. And I want you to see how much you can set this up on exercise 12. So go ahead and let's take a break and see how much you can do here. All right, so hopefully you got some leeway on this. So I just started by writing down my equations, my dissociation equations, and I put down the concentrations of each of these, which I got from my problem. I then debated, which one do I use first? Do I do this one or do I do this one? How do you know which one that's going to give you the most H plus? The larger Ka. The one that has the largest Ka is going to give you the most H plus. So HNO2 has the largest Ka, so you want to do this one first. So set it up, solve for x. Remember what we can do, we can get rid of this x because we're assuming it's really tiny. So solving for x, it comes out to be 0.045. pH equals negative log of H plus. So your pH equals your 1.35. First part of the problem done. Now you have to go back, and to figure out the cyanide, you have to do another rice table. But this time, you know what H plus is. It's 0.045. You do have 0 cyanide to start out with. This is minus x, and these are plus x, just like normal. This is 1 minus x. This is 0.045 plus x, and this is x. Set up your Ka equation. Ka equals 0.045 plus x times x, 1 minus x. Wow, this looks like a doozy. Well, remember, what can we do? Well, we're given our Ka, and we're assuming that these x's are so small that we can get rid of them. So now our problem simplified a lot. It's 0.045 x over 1. Our x comes out to be 1.4 times 10 to the negative 8th. Now guess what? I didn't write what my x was equal to, like I did over here. So I go back, I look, I'm like, oh, x is equal to Cn negative. So I'm done, because that's what I was asked to find. Concentration of the cyanide ion. All right, you're going to start seeing patterns left and right here. Why don't we stop again? Why don't we sit there? And now we're trying to figure out the percent of dissociation. So the percent of dissociation is always your H plus divided by your original acid concentration times 100. All right, so these are weak, so we don't know what they're equal to. So we're just going to set up our equations here. We know this is 1, this is 0, minus x, x, and x, 1 minus x, x, and x. Set up your Ka values. So it's H plus times C2H3O2 negative divided by HC2H3O2. Put in your values. 1.8 times 10 to the negative fifth. These are both x. And this is 1 minus x. What do we always do? We get rid of this x. Much easier to solve for. Now our x is 0.0042, but we're trying to find the percent of dissociation. Remember what your x is equal to? H plus. So, take our H plus, divided by our original acid concentration, that should be HC2H3O2, times 100. So 0.0042 divided by 1 times 100, and that's 0.42%. A lot smaller than those strong acid dissociations. You can try the next one on your own, and you know you should get 1.3%. All right, let's do another one. This one, I'm probably going to have to get you started. You know your equation. You just take your acid and you break it apart into H plus C3H5O3 negative. All right. They know that they give you 0.100 molar of this, and you don't know. Oh, this is easy. They tell us how much it's dissociated. Well, let's write an equation and see what we can get from that. 3.7% equals H plus times your acid times 100. That was our dissociation equation. We know this, so 3.7% equals H plus divided by 0.100 molar times 100. Make H plus your X. X comes out to 0.0037. Well, X equals, if we would have set up our little chart, X equals those. Our H plus and our C3H5O3 negative. Well, let's set up a Ka. You know this is going to be minus X, 0.100 minus X. Ka equals H plus times C3H5O3 divided by your acid. Guess what we're going to do? We're going to ignore our bottom X. So we have X. Ooh, we have values for those. We have 0.0037 times 0.0037 divided by 0.100. Like to use those brackets, and that's how you get your Ka. Remember what I did there. I know I keep repeating it, but we're assuming that this X is so small that we don't use it. All right, you're going to find out that the same thing is true for these bases. So I'm going to work out some bases, and it's just with OH, and I'd like you to work out some bases, and then I'm going to just pull them up on my screen. Okay? All right. Start working on those examples, starting with exercise 15. Here's my answer for this one. This is exercise 15. You know it's a base, so you know hydroxide has to be produced, so react it with water. Bases accept protons, so this is going to be accepting my H plus to become NH4 plus. Where does it get that proton at? From the hydrogen and the water, and then you're left with OH negative. We don't ever have to worry about this because this is a liquid and we always ignore it. Set up your race table, set up your KB equation, ignore this X. X equals OH negative for this one. That's where you're going to make your mistake. Once you find your OH negative, you can find your POH, and you know POH plus pH equals 14, and you can find your pH. On to the next one. Okay, we're back. So this one, you probably read it and got a little bit scared because you're like, oh my God, I don't know what methylamine is. It doesn't matter what methylamine is. Methylamine is this, but say you don't know what methylamine is. You can still, first of all, you know it's a base. How do you know this is a base? Because they give you the KB of it. That's the first thing you see in the problem. So you know methylamine's a base. So we always react our bases with water. So even if you don't know what methylamine is, make it Ma. What do bases do? They gain protons. So, okay, let's make it MaH+. It just gained a proton. Where did it get that proton from? The water. Once this water loses a proton, then you're left with OH negative. You could have wrote this equation like that. It doesn't matter. Do your race table, which you're experts at. Do your KB expression, which you're experts at. Get rid of this X because we're assuming it's so small. That X is equal to the OH. Always have to check that. That's where you're going to make your mistakes. Now that you have your OH, find your POH. And now you know pH plus POH equals 14. Not bad, right? All right. Here's a little bit of reading for polyprotic acids. Acids with more than one hydrogen will ionize in steps. Each dissociation has its own Ka value. Biggest thing to take out of that is that the first dissociation will be the greatest. So the first proton that comes off will have the greatest concentration. As each H is removed, the remaining acid gets weaker and weaker, and therefore has a smaller Ka value. And you can just take a gander at this, and you can see how the Ka values decrease as the number of protons come off. So this has 3 protons in phosphoric acid. Remove the first one, that's your Ka. Remove the second one, that's your Ka. And remove the third one, that's your Ka. All right, so this next thing, I'm not going to concentrate on exercise 17 and 18 because you need the quadratic for it. And I was told you do not have to do the quadratic for the AP test. So let's take a break and let's do 19. You do it, and then I'll show you my answer. All right, here we go. So first of all, we're starting out with sulfuric acid. Strong acid. So that means it ionizes 100%. So it's going to ionize into H plus with the same concentration and HSO4 negative with the same concentration. You only take 1 proton off at a time. So now the next step, you have to bring your HSO4 down and ionize it again. Take another proton off. So now you have H plus SO4 minus 2. We didn't have to do a race table here because this was a strong acid and it ionized 100%. We have to do a race table here because we don't know how much it ionizes. We do have a value of this that we get right there. We have a value of your H plus that we get right there. We do not have SO4 negative 2. Set up your race table. This is minus X, this is plus X, just like usual. Don't let this number scare you. Ka equals products over reactants. Where did I get this number from? You have to look up the Ka value for HSO4 from your table 14.2. Plug in all your values, but remember what we do. We assume that that x is so small. So now we're just solving for x. X equals your H plus. Your comes out to 1.2 times 10 to the negative 2. pH equals negative log of H plus. So it's 1.92. And there we go. My next video is going to be titration curves and acidic salts. Just as fun. Then afterwards we get into buffers, and that's probably the hardest part. All right, have a nice day.